In today's lesson, we're going to finish talking about hypothesis testing and confidence intervals, and we're going to finish this by looking at the difference between population proportions, right? So we've seen the differences between population means. We saw that with large samples slash normally distributed ones. We saw that in small samples. We saw that with paired data. Now we're going to look at it with proportions. So with today's lesson, all we want to do is consider how we do hypothesis tests or confidence intervals for the two sample tests of proportions. Right? So if we have two different samples, they're going to be independent. We want to use proportions here. So we have assumed that sample means on continuous data come from normally distributed populations, and we've seen how to form those intervals. We also saw how to do this with proportions in the single sample case. What if we had two samples of binomial distributed data? So we have two different proportions that we're trying to estimate or trying to make inferences about. So we'll assume that X comes from a binomial NP1 distribution. Y is coming from a binomial MP2 distribution. So again, the N and the M do not have to be the same. We'll assume X and Y are independent of one another, right? So this isn't paired data. This is going to be two separate independent samples. And we want to know about the difference P1 minus P2, or P2 minus P1. Of course, it's exactly symmetric. Now, we can use the same difference estimator that we might think to use, right? So we know how to estimate the proportion P1. You just take the total number of successes divided by the total number of trials. We know how to do the same thing in our second sample, right? And so then, just like we did with means, we can consider just the differences between those two proportions. If we work that out, the variance will also just be given by the sum of the two different variances, right? So the variance of X is going to be P1 times 1 minus P1 times N, and then P2 times 1 minus P2 times M. And then if we are actually doing the difference in proportions, each variance will be scaled by the respective sample size. Now, as long as the normal approximation would apply to the binomial, each of them individually, then we can use a joint normal approximation here to form confidence intervals and hypothesis tests, right? So confidence intervals are going to be constructed in exactly the expected way. Now, with hypothesis tests, there's sort of one interesting or perhaps strange scenario, and that's we can only test one hypothesis in this case, right? And that's the hypothesis that P1 equals P2, or that their difference is exactly equal to 0. And the reason for this is that if you're actually testing a different difference there, the approximation that we're using sort of starts to fall down. And you could work out what the approximation would have to be if you wanted to test different differences. In practice, we're almost always going to want to test that the difference is equal to 0, right? And so because of that, this isn't actually going to be a big hurdle in practice, but it is worth noting that for the first time, we have a restriction on what hypothesis we can test. We can do either one tail as well, but we have to sort of rely on the equality being the test that we're running there. Now, if we were to assume that the variances or that the proportions were equal, then we would have variance given by P times 1 minus P times by 1 over M plus 1 over N, right? And so that's if we have this common proportion there. And so then we can get what the variance would have to be under the null distribution. And then what we can do is simply apply our normal or the normal approximation as we would be used to doing it, right? And so we would form the statistic, be P1 hat minus P2 hat minus 0, scale by the standard deviation. Again, whenever we're doing binomial populations, if we don't know what the true proportion is going to be, then you can take P equals 1/2 to be conservative, and then you use your normal tests in exactly the way that we've been doing it, right? So if you want to do a confidence interval, it's going to be plus or minus the critical value times by the standard error. If you want to do a hypothesis test, you're going to look into which tail is the relevant tail, add up the p-values from there. Walk through the process exactly the way that we've seen all of these times up until now, right? So two populations from independent binomial distributions can have their proportions tested. through sort of the simple differencing procedure, so long as we're assuming that they're independent and that the test that we're running is that the proportions are equal. So that's essentially everything that we wanted to cover in terms of hypothesis testing, right? So we saw the general framework, we saw many specific iterations, we saw how we do it with one sample, we saw how we do it with two samples. And I think the key idea to take away is that every sort of specific iteration of this is going to sort of feel the same, right? Once we know what the sampling distribution is, the rest of it all plays out in exactly the same way. And so the trick is just, how do we get to that sampling distribution? And really the factors we're considering is, what's the underlying distribution? How large is the sample? Do we know the variances or not? Right? And with those questions, once we know, are we using a normal distribution here? Are we using a t-distribution here? We can get to the actual hypothesis testing or confidence intervals. In the next few lessons, we're going to start looking at linear regression, which will be the final topic that we're covering in this course. And so I hope to see you all in these last few lessons here.